All right, I had a question on problem number 6, and I wanted to take time to go over this a little bit more in detail because the response I gave in email was correct. However, this problem is actually located in the section as far as if you look at the homework problem sections, it's listed under, nodal analysis. Now, it didn't specifically say that you had to use nodal analysis to solve this problem. So the question I received was about using loops, which is technically a perfectly acceptable way to solve this problem. But I also want to show how you can do this with nodal analysis, since I didn't get an opportunity to go over that in yesterday's Tech Live session. And so what I'm going to do is I'm going to discuss the loop situation here and the nodal situation, but I'm going to do it with a different problem here. And you might say, why did I draw this problem if I'm not going to do this one? Well, it's your homework problem, and I would rather do a problem that's very similar to the homework problem, but that has that's different, so that we can solve it all the way. Okay, so this is actually problem number 5 then. So this circuit here looks like the following. And this is 2 ohms. Now this problem, if you read it in the text, it does specifically says using the nodal analysis technique to determine I using nodal analysis. Now, nodal analysis or KCL is actually used to find unknown voltage, is actually normally used to find voltages. So let's look here and see some voltages that are labeled here. Now these were already labeled in the diagram, this V1 and V2. Now I'm putting a circle here indicating it, and I'm going to kind of emphasize again just to try and show you that this here is all one node. It's all one node connected because it's just all a wire. And similarly, this that I've labeled here, this is all one node here. And so we're going to use KCL to find, or nodal analysis, we're going to use this to find V1 and V2. Now I know you said, but the question's asking us to find I, and we'll get to that, but we will first use nodal analysis to find those voltages V1, V2, and I forgot to label what this current was. It actually is 5 amps. Now, what I like to do here, there's a couple things here to remember here with KCL. KCL says that there's two ways to think of it. There's technically three. Current entering node equals current leaving node. Current if we draw all currents leaving node, they sum to 0. And then the third one is very similar to the second one. And that's if we draw all currents entering node, they sum to 0. All right. So that's KCL, and then nodal analysis we use here. Now you might say, it looks like I'm dealing with currents. How do I find unknown voltages using this? Well, because what we do here is we use Ohm's law to convert the currents to voltages in our equations. That's how it's typically used to find unknown voltages. All right. I don't want to scroll down here, so, well, if you haven't copied all of that down yet, I would just go ahead and pause the video. I'm going to erase all of this here so I don't. And I'm going to see here, I'm going to erase this little blue one so that I don't get my diagram all messed up here. So, okay. So what are we going to hear? So I'm going to also, for now, erase this current that I'm looking for, just because I don't want to get this current confused with everything else that I'm doing here. So what we're going to do is we first are going to determine how many nodes we have in this problem. That's always a good place to start. And the number of nodes, we have 3 nodes. And remember, a node is a connection point between circuit elements. Well, this is, I'll just label this, well, I won't label it, but this is one node up here where V1 is. So again, here, I'll highlight it. So this is one node right there. This is a second node right there. And then the third node, which sometimes people forget about, is the one that's, at the bottom right here. So that's my third node. Now, this is one thing I personally don't like about how the textbook draws their circuits, is that my philosophy is that you should always draw a ground in your circuit so you know where your reference is as far as how you're measuring things, as far as what you're considering to be 0 volts. And so we don't have one here, so we should put one in. Now technically we can put it anywhere, but we want to make life easy for us. So the one that makes the most sense is putting the ground in down here. And remember, the ground, I know then what that voltage is. Ground is 0 volts. Now there are different types of grounds, which we'll talk about in another course. There is like, earth ground, there's like kind of floating grounds and all sorts of other things. And for now, we're not going to worry about all that stuff. That's just ground, and we're going to consider that 0 volts. Okay, so then I have two unknown voltages. I don't know what this V1 is, and I don't know what this V2 is. I don't know why I just circled those, because I'm going to just promptly erase them. Now, at each node, we're going to sum up my currents here. So I'm going to do here, and I'm going to say this, in fact, I'm going to label this here. I'm going to change this from V1 to VA and VB, and you'll see why I do that in a second. And so what I'm going to do here is I'm going to say I'm going to look at node A. And then let's draw all of the currents either entering or leaving the node. Now, rule of thumb here is I always draw my currents when there's resistors leaving the node that I'm working on. So I am working on node A, so I'm going to draw my currents leaving that are dealing with this 1 ohm and 5 ohm resistor. I'm going to draw them leaving the node. Now what am I going to do? Well, I'm going to look at this 5 amp, and the arrow's already kind of going in a direction, so I don't want to have to turn it around because then I have to deal with negative signs and everything. So that one is coming and entering this node. So we can now write an equation. Let's label these here. I'm going to label this one I1 and I2. And that's kind of why I changed the labels of V1 to V2 to VA and VB. So node A here, well, the current entering the node has got to equal the current leaving the node. So what do I have? I have 5 amps entering the node, and that's got to equal I1 plus I2. Now we will work on this equation some more in a second, but before we do that, let's go ahead and just go over to node B, because that will be another one that's easy here for us. Now node B, I am going to draw currents again for node B, but remember, whatever node I'm working at, I'm going to draw the currents going in the direction of leaving if they're going through a resistor. And I'll go ahead and label these I3 and I4. Now, I2 and I3 are going to be essentially the same number, but they're going to have, one's going to be positive, one's going to be negative. And now, in this case, all of my currents are leaving the node because I'm going to keep this one here just leaving because it's leaving already. And so for node B, I would have the equation I3 plus I4 plus 4 equals 0 because they're all leaving the node. Okay, and you'll see why I draw my resistors, the currents going through my resistors at a node such that they're always leaving in a second. Now, before we get into that, let me go ahead and show you how you determine, or how we're going to use Ohm's law to actually compute here. So, let me draw a resistor here. And then it's connected up to a bunch of other circuitry. I don't care what it's connected up to. It's connected up to a bunch of different circuitry. So let's say that we have a voltage here Vx and a voltage here Vy. And then we have some resistance R. Well, the voltage across this resistor is not Vx or Vy. the voltage across the resistor is Vx minus Vy, because these are the node voltages. So they're the voltages as if you were measuring with respect to ground. They're not the voltages as if you were measuring across the resistor, because if you're measuring across the resistor, like having the positive red cable of a DMM and the black cable of a DMM connected across that resistor, you're literally taking the voltage at point X, subtracting the voltage at point Y in order to get the voltage drop across the resistor. So that's going to be important here on how we're going to use Ohm's law, because really our Ohm's law is going to be, and I'm going to kind of put it in parentheses here, and I'll draw my current. I'll just call this I. It'll be Vx minus Vy, because that's my voltage across the resistor, is equal to my current times my resistance, which this is really going to be the important equation that we're going to use a lot. That the current we can write as the voltage at X minus the voltage at Y divided by the resistance. Now, the cool thing about the way, if you always draw it with your arrows going this way, another way you can think about this is it's the voltage at the tail. It will always be voltage. Let me actually get a pen here. It will be voltage at tail minus voltage at pointer over the resistance. So this will be voltage at tail will be node you are in. Okay, so instead of kind of waving my hands and writing more stuff down here, let's actually apply this back into this problem here. So let me go ahead and again erase some of this, just so I can go there. And so what we have here is we have, let's look at I2 for instance. And you'll get used to these and you won't even necessarily write this equation down this first step here. But I'm going to even just kind of write this here. So I get 5 is equal to, I'm going to leave a space for I1. I'm just going to do I2 first. So it would be plus, and then what I do here is, okay, I2 is going through this 5 ohm resistor. I'm currently in node A. So I start with this voltage here. I start with VA. I subtract the voltage at the other side of the resistor. The voltage at the other side of the resistor is VB. Then I divide by the resistance, which almost looks like a 6 there. Divided by 5. So that's for I2. Now I1 is in a lot of ways even simpler than what we just did there. I'm going to do the same procedure though. Okay, so my 1 ohm resistor. So I'm going to start at the node voltage, VA. I am going to subtract the voltage at the other side of the resistor. So that's this voltage here. But wait, that's ground. So that's 0 volts. So I'll go ahead and write it just to be complete. So I have VA minus 0 divided by my resistance, which is 1. Now, the way we're going to simplify this equation here, I know that there's just a 1 here, and I could just ignore that. But what you want to get in the habit of doing is you're going to want to clear your fractions out. And so you're going to either want to think of least common denominator, or a simple way is just, multiply these two numbers together and multiply both sides of the equation by it. And what do I mean here? Well, I'm going to multiply both sides of my equation by 5, because that's 5 times 1 is 5. Now if I do that, what happens here? Well, I have to multiply everything by that. So I'd have 5 times 5 on the left-hand side, 5 times VA minus 0, because if I divide by 1, I don't get anything. But then notice here, if I multiply this by 5 here, I would wind up with just VA minus VB, because the 5's cancel out. And so I wind up then with an equation that's 25 is equal to 5 VA plus VA minus minus VB. So that would be 25 is equal to 6 VA minus VB. Now, if I go to node B here, do the same thing, I'm going to start off a little bit quicker here. Well, what I'm going to do here is I3, that I'm in node B now, so I start with the VB. So I have VB minus VA divided by 5. And then I4 would be VB minus 0 divided by 2. And then I'll go ahead and move the 4 to the other side, is equal to negative 4. So in this time, I'm not going to multiply it by 5, I'm going to multiply both sides by 10, because that's what 5 times 2 is. So let's see what happens there. So I'll have 10 times VB minus VA over 5 plus 10 times VB minus 0 over 2 is equal to negative 4 times 10. And then some simplification. 2 becomes 1. This becomes a 5. This becomes a 1. And that's the whole point, is we're getting rid of all of the fractions. And so what I'd have here is 2 VB minus 2 VA plus 5 VB is equal to negative 40. And so we'd wind up with minus 2 VA plus 7 VB is equal to negative 40. Now we just have a system of equations with two unknowns that we need to solve. And so I'll write this here as 6 VA minus VB equals 25 minus 2 VA plus 7 VB equals negative 40. Now, you can solve this however you want to. What I'm going to do is show you that you can solve this just by some basic algebra. And so what I'm going to do here is I'm actually going to multiply this bottom equation by 3. And so I'd wind up with top equation being 6VA minus VB equals 25 minus 6VA plus 21 VB is equal to negative 120. Then I'll add those two equations together. 20 VB is equal to negative 95. So negative 95 over 20, which, let me pull my calculator up here. Why is it not doing, oh, it's in the second button. What is going on here with my calculator? There we go, negative 4.75. VA would be, just using any one of these equations, I'll say 6 VA minus negative 4.75 is equal to 25. So solving that, we get VA is equal to 3.375. I hope I didn't make any stupid arithmetic errors along the way here. I think I'm good. We're going to find out soon enough if I made an arithmetic error. So let me scroll back up here. So 3.375, negative 4.75. Is this 7.5? I have such a bad short-term memory here. Yeah, 4.75. So those are our voltages. So I'm going to clean up my circuit diagram a little bit here. Erase some of this stuff here. I'm just wondering here if I could do a cheat here. No, that's not what I was looking at. If I was making super professional videos, I'd be editing all of this stuff out, but that's not what I'm doing. All right. So let's go back to what the original problem was asking me for. I mean, we were supposed to use nodal analysis techniques, which we did to find these unknown voltages. But the problem was asking us to find this current I going that direction. And to find a current going through a resistor, you start with the voltage at the tail, subtract the voltage at the pointer end, and then divide by the resistance. And so this current I would be 3.375 minus negative 4.75 divided by 5. And so let's use our calculator. And we would get 1.625 amps. So I'm going to write that off to the side here. And now, after going through all of that technique for nodal analysis, and I know this is a longer video, but that's okay. Now, this problem did state that it wanted us to use nodal analysis, but if we think about this for a second, now, if a problem says use nodal analysis, you need to use nodal analysis. You can't just decide, well, I'm going to do mesh analysis instead. But if a problem doesn't state it, you can do it anyway. Now, I would encourage you to try and do problem 6 using nodal analysis. Even though problem 6 doesn't state that, I would encourage you to do that. Although I will show you the quick way you could verify your answer to make sure that your answer from doing it the first way is correct. So there's this current I, and I'm going to draw a loop here that's what we're trying to find. So I'm going to call this loop, and I'm going to purposely label this I2. So I'm going to draw two other loops here. I'm going to draw a loop that's in the direction of this arrow here. So I'm going to draw in the direction of this current supply. I'm not just going to draw it clockwise because I always draw my loops clockwise. I'm drawing it clockwise because that's the direction of this 5 amps. So I'll call this I1. And then I'm going to do the same here. Now, because only one loop touches the two current supplies, we know that, for instance, I1 is equal to 5 amps and I3 equals 4 amps. Now, why is that a big deal? Well, it will make this loop inside much easier, and we'll see that in a second. Now, I'm going to put this out here. If I had some other components off here like this, there would be another loop here, I4. And now you could not say I3 does not equal 4 amps and I4 does not equal 4 amps. You have to look at the direction. Well, I3 is going in the direction of the 4 amps. I4 is going in the opposite direction of the 4 amps. So it would actually be I3 minus I4 is equal to 4 amps in that case. So you can't just automatically assume that that works all the time. So you do have to pay attention to that. The idea is always knowing whether you're touching one loop or not. Okay, so we're touching one loop. So we're good. So I'm going to write an equation here for this loop 2 here, for that I2 loop. And so we have the voltage across the 1 ohm resistor, plus the voltage across the 5 ohm resistor, plus the voltage across the 2 ohm resistor, and that's all the voltages. There's nothing else there. And that has to equal 0 volts. Now, using Ohm's law, just like we did in the Tech Live yesterday, we could have 1 times, and this would be I2 minus I1 plus 5 I2 plus 2 times I2 minus I3 equals 0. But then what do we have? Well, 1 times I know is going to just be that. So I get I2 minus 5 amps, because that's what I1 is, plus 5 I2 plus 2i2 minus 4 equals 0. And so everything here works out where I only have a single equation, one unknown, and so I'm just going to hopefully do the arithmetic correctly here. And so this would be 8i2 is equal to 13. And so this would get me I2, pulling out my trusty calculator, 13 divided by 8, which is, of course, 1.625. And you better believe we should get the exact same answer, which is why I took a second before moving on, because I wanted to double check all my work to make sure I didn't make a stupid arithmetic mistake, which I'm prone to be doing those types of things. Because it shouldn't matter what analysis technique you use, you should always get the same answer. And if you don't, then we've invented some kind of new electrical engineering theories, which, you know, I'll insult myself as well, saying it's like, yeah, and we're not going to be doing that in a course like this. So anyway, hopefully this helps not only with this particular homework problem, but also gives you a good example of how to do the nodal analysis as well.